Alright, so this is a video on some of the important things from the material testing thing. It can be some other tough problems. This is another sort of mathy one, but the concept I want you to understand behind it before you do the math. So I wanted to get down here to where we're talking about tensile testing. We have some simulations. Normally there was a program in Flash that could do this, but Flash is gone now, and I'm sad. But basically, we have these things called dog bones, and they're made of certain materials. And what's crazy is, if you know the exact material, and you know the diameter of the cross section, then you can predict exactly how much it's going to stretch before it breaks. And there's different materials that stretch more before breaking, or they break immediately. So these are called dog bones, and they're a uniform shape that companies use, not companies, materials testers, materials scientists use to be able to test and compare objects, because you can test how much can I stretch this and it'll still bounce back to its original shape. How much can I stretch it before it breaks? And basically a tensile test is when you pull something until it breaks. So here's what it looks like. The more force you apply, delta is change in its elongation. So you're applying more and more force, and when you see this graph go to the right, it is, imagine your dog bone stretching, or your material stretching. So it goes up at a pretty straight line for a little while, and then it flattens out. Once you get to this area right here, it's the point of no return. So here, oops, I'm scrolling the wrong way. Hold on. But one thing to know is, if you have two different sizes, then their force graphs are different. So it's kind of weird, but basically, because we don't want to compare, like this would take a lot more force to break than that, but if they're made of the same material, they should have a very similar graph. So instead of having it based off of just how much force it takes, scientists had to come up with a different way. So no matter what, let's say this is brass. If this was a little brass piece and this was a big brass piece, they wanted the same exact number to show up as far as how much it took before it could break, or how much it took before it reached that region where it would never bounce back. By the way, the region where it does bounce back is called elastic, much like an elastic rubber band would bounce back. And the part here where it doesn't bounce back, it's not broken. I mean, it's not broken until here. There's their failure point. But this is called the plastic deformation. That means it'll never go back to its original. So anyway, what scientists wanted was, they wanted the same number no matter what if you have a piece of brass. They wanted the same number if you had a piece of steel. So what they did was, they took the amount of force it took and divided it by your area, and that made the same number. So if you had a big hunk, it took a bigger force, but it had a bigger area, so it made the same stress. If it had a tiny force on a tiny area, it made the same number for stress. It's basically force divided by area. That's not bad. It's called stress. So if you said how much stress is on a dog bone with the 430 pound applied force, all you got to do is do the force, 430, divided by the area of this shape. You have to imagine it's a cylinder, so if I sliced it, I'd be looking at a circle, and its diameter is 1.25 right here. Okay, so you can figure out the stress on a dog bone that has a certain force, and then it's 35,000 psi, which is pounds per square inch. That's a typical thing we do. So the other part of that is how much strain. So how much is this material pulling? Because if you had a really, really long, imagine you had a beam that was 20 feet long, and you applied some stress to it. That's going to stretch a lot more before it breaks compared to a 2-inch piece. So basically, to even things out, so it doesn't matter if you have a tiny piece or a big piece, we want to get the same number. You take the amount of stretch, which is, that's a lowercase sigma, or sorry, lowercase delta. Looks like that. It's kind of like a musical note almost. Lowercase delta divided by your original length. That's why you see an L with a little O below. This is your original length. Might be a 0 for time 0. So that's your strain formula. So there's stress, there's strain, and it fits this curve. It looks a lot like that one, right? But it used to say force and elongation. If you see this graph, it doesn't matter if you had a big piece or a little piece, or if it took a ridiculous amount of force or a tiny amount of force. This graph is your basic graph for any shape. It's just, it doesn't matter if it's a huge hunk or not. So here's the important points. You have to know some important points on this graph. Whenever they test a material, one of the first points they look for is the elastic range, because your initial amount of stress versus strain or force is a straight line or linear. And during that whole time, if you let go, the piece of metal would go back to its original size. No harm, no foul. So for this whole time, the elastic range, that means it'll bounce back. So if you let go anytime in here, it snaps back. And that's, it's stretching here. It's weird to think, but if you think about bridges getting warm and bridges getting cold, they're stretching out and pulling back, and they don't break. So they have a certain amount of stretch to them. Directly next to it, I know it looks like the exact same spot, and for me, it's pretty much the same, is the proportional limit. Oh, that's the same part. Hold on. That's where it stops the straight line, elastic, it'll bounce back. Oh, remember that E, that modulus of elasticity we used when we did beam deflection? That can be found by taking your stress divided by strain, or your Y, because remember, stress is your Y, divided by your X on the slope. It's the slope of this line. So if you had the slope of this line, you know the modulus of elasticity for that shape. A measure of stiffness that like we could use with a board or a diving board or something, if you just calculated the slope of that straight part of the line when they're doing a tensile test, you could figure out what its modulus of elasticity was. So that's kind of crazy. So one point is called the proportional limit that you got to know. That's when it switches over from being able to snap back and not. Okay, and then the slope of that line is your E. Here's your elastic limit. Right after that is called the yield point. That's when it starts to give up. So right here, your piece of metal is fighting the good fight. And then after it gets the elastic limit, if you let go of it again, it won't go back all the way to its original shape. Okay, so like imagine you had a dog bone, you're stretching. If you let it go here, it's going to go back. If you let go here, just past there, it'll go back and maybe be a millimeter longer than it should be. And that's called the elastic limit or yield point. Okay, it is almost in the exact same spot, but technically it's a tiny, tiny bit above it. So the proportional limit is just below it. That's where it behaves like a straight line. One dot past there is the elastic limit. That's where it's not going to bounce. The very last time where it could bounce back. The point of no return. This is called resilience. If you find the area under this curve, it is the amount of energy that it can absorb and bounce back. Why is this important to designers? A car bumper, they would want to make sure that if somebody just bumped into your car bumper, it would spring back to its original shape. Like, you wouldn't want a little kid on a tricycle to bump into your car bumper and it be dented, so you got to fix it. So it's got to have a certain amount of resilience, and you can calculate the resilience of any material that you've done a tensile test in by just finding the area under here, which is a triangle. You can find the area of a triangle. Okay, and then that's the elastic limit. It's called the yield point or elastic limit point. So right below here we have the proportional limit. That's where it behaves like a straight line. The next dot over, we call it the elastic limit or yield point. That means when I just start to put a little more force, it starts to stretch more. See here, it's fighting, and now it gets out wider. Okay, don't worry about that one. This chunk here, so if you snap back in this chunk, it's called elastic deformation. Here it's called plastic deformation. This animation actually showed it pretty well. It would stretch out, and then it looks like it snaps back, but it's longer than it was before because you've stretched it. And I know you've probably done that with, heck, even with rubber bands. If you stretch them out enough times after wearing them in your hair or something, they don't ever go back to the original size. They're still stretchy, but they don't go back to the original size. That's because they've undergone plastic deformation. Okay. Basically, until here to here, that right there at the end is your failure point. So, this very top point has a special point you got to know too. Oh, here's something it does right before it breaks. Sometimes it does this shrinking in right before it snaps. It's called necking because it looks like a person's neck. Okay. And basically, why on the way up, it's fighting, it's getting harder and harder to break, and then here, it's still not broken yet, but it's getting easier and easier. See how the force goes down? So that's because it's stretching and it's like starting to give up. It's like, all right, I'm going to hang on for a little longer, boom. So this is right up here is where the necking starts. And that point at the very top, where is it? It's called your ultimate tensile strength. I don't know where it was in here, but we'll put it in the thing. And then that's called your failure point. That's where it's going to break. And the amount of stretch it has before it breaks is called its ductility. So if you had a piece of like gold is very stretchy. It's ductile. If you had a piece of cast iron, it barely stretches at all. The thing would look like this. It would go straight up and then break right there. Because cast iron does not stretch much. If you've ever dropped a cast iron pan while camping, they can just shatter down the middle on a straight line. If you had a piece of brass or gold or something like that, they stretch a lot before they break. Here's a few different ones. That's what cast iron looks like. It just snaps off. This one's aluminum. See how it stretches a lot before it breaks? And this one's steel. So yeah, here we go. This is what it would look like for cast iron, where it goes up and snaps. This one is more like aluminum, where it stretches, and then breaks. And then toughness is how much area is under the entire thing. You would need calculus to be able to find the area under this crazy curve, but it's doable. And basically, however tough a material is, so you would say cast iron is not that tough. It has a pretty high force, but since it doesn't stretch and it breaks so easily, you wouldn't call it as tough. So it's kind of a combo of how much it can go up force-wise and then how much it can hang on. That's your toughness. All right, so we'll look at these examples in class. Anyway, so then there's other testing. You can read about that, all these different tests, and there's some videos you can click on. All right, hopefully that explains some of the stuff, and there's important points we have to know, and then we'll do some calculations in class. All right, people, I will talk to you later.